Welcome to Module 5, Chapter 15, on Emerging Technologies Transforming the Circular Economy. In this chapter, we will explore how cutting-edge technologies are driving innovation and change within the circular economy. Our focus will be on three major technological areas: artificial intelligence, blockchain, and the Internet of Things. These technologies are reshaping how resources are managed, improving efficiency, and enabling new models for sustainability. We will look at how these tools help transition from traditional linear models, where products are made, used, and disposed of, to circular models that prioritize reuse, recycling, and regeneration. Through practical case studies in textiles, e-waste management, and plastics recycling, we will see how these innovations address real-world challenges and create opportunities for more sustainable practices. In this chapter, we will begin with an introduction to emerging technologies in the circular economy, setting the stage for understanding their impact. We will then examine how artificial intelligence and blockchain are driving innovations in the textile industry, focusing on improvements in resource efficiency and supply chain transparency. Next, we will discuss the economic and strategic impacts of digital transformation in textiles, including how these changes affect business models and sustainability. We will also address the challenges and broader implications for the textile sector, considering technological, organizational, and cultural barriers. The chapter continues with a case study on blockchain for e-waste management, highlighting India's e-Pragati initiative and its role in improving transparency and compliance. We will then explore IoT-enabled plastic waste recycling in Thailand, showing how real-time monitoring and data analytics optimize recycling processes. Finally, we will conclude with key findings and strategic insights for advancing sustainability in the circular economy. Artificial intelligence, blockchain, and the Internet of Things are transforming the circular economy by enhancing resource efficiency, traceability, and real-time monitoring. Artificial intelligence analyzes data from IoT devices to optimize resource use and improve waste sorting, making recycling processes more effective. Blockchain technology secures transparent and immutable records, ensuring that materials can be traced throughout their life cycle and that accountability is maintained across supply chains. IoT sensors provide real-time monitoring of products, enabling better decision-making in recycling and recovery. The integration of these technologies creates robust circular systems that are both efficient and trustworthy. By combining AI's analytical power, blockchain security, and its connectivity, organizations can move from linear models to circular ones, reducing waste and maximizing resource recovery. This chapter will illustrate these concepts through detailed case studies, helping you understand how technology drives sustainable change. This chapter presents three detailed case studies that demonstrate the application of emerging technologies in different sectors and regions. First, we will look at the textile industry in Europe, where artificial intelligence and blockchain are used to enhance circularity and promote sustainable practices. The collaboration between the Ellen MacArthur Foundation and SAP serves as a model for integrating digital tools with circular economy principles. Second, we will examine India's e-Pragati initiative, a government-led project that uses blockchain to improve transparency and regulatory compliance in e-waste management. This initiative shows how digital transformation can address chronic inefficiencies and support environmental governance. Third, we will explore how SCG Chemicals in Thailand leverages IoT technology to optimize plastic waste recycling and increase material recovery rates. These case studies highlight both the potential and the challenges of implementing advanced technologies for circularity, providing practical insights for future sustainability efforts. The partnership between the Ellen MacArthur Foundation and SAP is a pioneering initiative that drives the textile sector's transition from a linear to a circular economy. By reducing waste and overproduction, this collaboration addresses systemic inefficiencies that have long affected the fashion and textile industries. SAP's advanced digital tools are integrated with the Foundation's circular economy principles to improve transparency and efficiency in supply chains. This partnership offers a scalable model that combines ecological regeneration with economic competitiveness, demonstrating how technological innovation can support sustainable business practices. The collaboration serves as a foundation for understanding how theory and practice converge in system-level sustainability transformations. It highlights the importance of integrating digital solutions with circular design principles to create resilient and regenerative business models in the textile sector. Artificial intelligence is revolutionizing textile production by optimizing demand forecasting, automating quality control, and supporting sustainable design. AI refines demand forecasting by analyzing large datasets, including historical sales and real-time inventory, to reduce overproduction and better align production with actual consumer needs. This helps minimize waste and lowers the environmental impact of manufacturing. Automated quality control uses computer vision systems to detect defects early in the production process, ensuring only high-quality products reach consumers and reducing the amount of waste generated. AI simulations also enable designers to model the performance of recycled and biodegradable materials, supporting the adoption of circular design principles such as designing for disassembly. These innovations not only improve efficiency but also raise important ethical considerations, such as the role of predictive analytics in decision-making and the need to address issues of control, bias, and trust in AI-driven processes. Blockchain technology is essential for ensuring transparency and accountability in textile supply chains. Every step of a garment's life cycle, from raw material sourcing to retail, is immutably recorded on the blockchain, making it verifiable and trustworthy. Consumers can access this information through QR codes on product tags, which link directly to blockchain records and provide reliable details about material claims, such as the use of organic cotton or recycled fibers. Smart contracts further automate the exchange of textile waste, supporting waste-to-resource platforms and enabling closed-loop supply chains. These contracts ensure that textile waste is diverted from landfills and repurposed into new materials. Blockchain also requires robust governance models to oversee decentralized peer-to-peer exchanges, ensuring that all participants adhere to agreed standards and practices. This technology builds reputational legitimacy and consumer trust, making it a cornerstone of circular supply ecosystems. Integrating artificial intelligence and Internet of Things systems into textile supply chains brings important data privacy and security challenges. Permissioned blockchain networks are used to ensure that only authorized participants can access sensitive supply chain data, protecting proprietary information while maintaining transparency for sustainability metrics. This balance between openness and privacy is crucial for building trust among stakeholders and encouraging wider participation in circular models. Ethical considerations also come into play, including the need to critically analyze issues related to digital surveillance, consent, and data ownership. As more data is collected and shared across supply networks, it is essential to ensure that all parties understand and agree to how their information is used. Addressing these challenges helps create a secure and trustworthy environment for digital transformation in the textile industry, supporting both innovation and responsible data governance. Economic incentives play a significant role in driving sustainable profitability within the circular economy. By tracking and classifying textile waste, companies can transform disposal burdens into valuable tradable assets through digital traceability. Partnerships with recyclers and upcyclers allow firms to convert waste into new inputs, creating sustainable value chains and secondary markets. Artificial intelligence further improves efficiency by identifying production bottlenecks and resource-intensive processes, reducing costs and environmental impact. The savings generated from these improvements can be reinvested into innovation or used to offer competitively priced sustainable products, enhancing market advantage. These strategies not only benefit the environment but also support business growth and competitiveness. By monetizing waste streams and collaborating across the value chain, companies can achieve both economic and environmental goals, demonstrating the tangible benefits of circular economy principles. Environmental, social, and governance criteria are increasingly used by investors to guide capital allocation, rewarding companies that provide verified sustainability data through blockchain-enabled reporting. Governments implement green procurement policies and subsidies linked to circular economy performance, incentivizing transparent and sustainable practices. Consumer preferences are shifting, with younger generations favoring ethical and eco-conscious brands that offer traceable, low-impact products supported by digital infrastructure. Loyalty programs and recycling incentives, powered by customer relationship management and analytics platforms, foster emotional connections and create new revenue streams. These strategies help companies build brand loyalty and improve their market positioning, while also supporting broader sustainability goals. By aligning financial, regulatory, and consumer incentives, businesses can drive meaningful change and establish themselves as leaders in the circular economy. Circular business models challenge conventional metrics by integrating environmental and social values alongside financial returns. Value in circular enterprises includes waste reduction, ecosystem health, and social benefits, not just profits. Calculating return on investment requires considering long-term ecological and social outcomes, such as improved resource efficiency and community well-being. Leading regenerative businesses embrace circular principles to foster resilient and sustainable practices, moving beyond short-term financial gains. Managers must adopt new approaches to performance measurement, recognizing the broader impact of their decisions on society and the environment. This shift encourages a more holistic understanding of value and success, supporting the transition to a regenerative economy that benefits both business and society. Implementing emerging technologies in the textile sector faces several challenges. Outdated legacy systems in many companies hinder integration with artificial intelligence and blockchain technologies, limiting the benefits of automation and data-driven decision-making. Organizational change is complex, involving high costs and employee resistance, as firms must redefine workflows and develop new skills. The lack of industry-wide standards for sustainability metrics and traceability protocols creates inconsistencies and undermines trust and scalability. Effective consumer engagement is also critical, requiring strong digital storytelling and visual labeling to support informed choices and drive change. Overcoming these challenges requires coordinated efforts across technology, organization, and culture, ensuring that all stakeholders are prepared for the transition to a circular economy. Systemic transformation in the textile industry relies on cross-sector collaboration among governments, non-governmental organizations, manufacturers, and technology providers. The focus shifts from incremental changes to transformative business models that integrate ecological and social outcomes. Regulatory alignment is essential, with initiatives such as the Digital Product Passport and the Eco-Design for Sustainable Products regulation requiring transparency on product composition, reparability, and recyclability. Proactive digital infrastructure enables companies to meet regulatory demands efficiently, turning compliance into a competitive advantage. By coordinating efforts across the ecosystem, stakeholders can drive sector-wide change and support the development of resilient and sustainable business models. Management theories provide valuable insights into scaling circularity in the textile industry. Institutional isomorphism, resource dependency, and socio-technical transitions are examined through the lens of sustainability, highlighting how different institutional logics interact and shape industry norms and practices. Leadership, policy, and digital innovation are identified as key enablers for expanding circular economy practices across sectors. The potential to replicate circular partnerships in industries with complex global value chains is explored, emphasizing the importance of adaptable strategies and collaborative approaches. By understanding the interplay of management theories and practical implementation, organizations can develop effective pathways for scaling circularity and achieving long-term sustainability goals. Digital transformation is revolutionizing e-waste governance, particularly in India's e-Pragati initiative. Historically, the e-waste sector faced informality, fragmented operations, and limited regulatory oversight. e-Pragati digitizes registries and automates compliance workflows, unifying data across state departments and enabling real-time monitoring of e-waste generation, movement, and treatment. Permissioned blockchain records all e-waste transactions, ensuring tamper-proof traceability and accountability. Each e-waste item is assigned a unique digital identity, allowing regulators to verify authorized processing and safe disposal. This approach improves transparency, supports regulatory compliance, and enhances the effectiveness of e-waste management systems. Blockchain technology is a cornerstone of compliance and institutional trust in e-waste management. Its immutability ensures that data, once recorded, cannot be altered, deterring non-compliance and fraud. Smart contracts automate regulatory processes, such as issuing certificates and triggering penalties, making enforcement more efficient and transparent. Blockchain builds confidence among stakeholders by creating systems that are both transparent and tamper-proof. Decentralized governance transforms traditional top-down approaches into rule-based ecosystems, where all participants are held accountable. This technology supports the development of trustworthy and resilient regulatory frameworks for e-waste management. Integrating blockchain into e-waste management delivers significant environmental and economic benefits. Improved traceability reduces hazardous e-waste leakage into informal recycling channels, protecting workers and ecosystems from toxins. Digitally enforced standards ensure recyclers meet environmental norms and recover valuable materials efficiently. Blockchain supports a secondary market by certifying reclaimed parts, encouraging reuse and local circular economy growth. Accurate reporting enables access to government incentives, promoting the formalization of recycling operations. These impacts demonstrate how technological infrastructure can support both regulation and market formation in sustainability transitions. Despite its promise, digital transformation in e-waste management faces challenges. Onboarding informal actors is difficult due to technological illiteracy, mistrust in government platforms, and high costs. Early data entry errors and inconsistencies hindered the development of reliable datasets. Scaling these initiatives requires training, stakeholder engagement, and regulatory reforms across regions and waste streams. Ethical and governance issues, such as data ownership, privacy, and consent management, must also be addressed. These challenges highlight the need for institutional learning and capacity building to ensure the success and scalability of digital public infrastructure for sustainability. Blockchain technology underpins smart regulation by enhancing trust and policy enforcement where traditional methods fall short. Digital governance integrates environmental compliance into daily government workflows, moving beyond external audits. E-Pragati exemplifies data-driven, participatory, and resilient governance frameworks that align with complex socio-political realities. Emerging technologies enable the localization of global sustainability goals within digital infrastructure and policy design. These innovations support the development of robust and adaptive governance systems that can respond to evolving environmental and regulatory challenges. The deployment of Internet of Things devices across the waste value chain enables real-time monitoring and optimization of waste collection. Sensors track fill levels and material types in bins, allowing for efficient routing and frequency of waste collection vehicles. Smart cameras and RFID tags identify plastic types, ensuring accurate sorting and processing of waste materials. Central dashboards provide managers with granular insights into collection patterns, enabling real-time operational decisions. These technologies improve efficiency, reduce carbon emissions, and support timely recovery of high-value plastics, demonstrating the power of IoT in waste management. IoT sensors monitor key operational variables such as temperature, moisture, conveyor belt speeds, and contamination in recycling facilities. AI-based quality control systems screen and divert non-recyclable materials, improving the purity and yield of recycled pellets. Automation and sensor integration reduce waste, enhance safety, and lower energy consumption in recycling processes. These innovations enable companies to meet quality specifications for high-value applications and support continuous improvement in closed-loop manufacturing. By leveraging IoT and AI, organizations can achieve greater efficiency and sustainability in material recovery. Digital twins and feedback loops are essential tools for monitoring and sustaining industrial operations in real time. Predictive analytics powered by IoT data help prevent equipment failures and optimize maintenance schedules. Early warning sensors, such as vibration, motor current, and temperature monitors, detect signs of machine wear or malfunction, allowing for proactive intervention. Analyzing historical data informs long-term trends and guides strategic investments for system resilience and efficiency. These capabilities support the development of robust and adaptable recycling operations, ensuring ongoing performance and sustainability. IoT-driven operations deliver strong environmental and economic results. Higher recovery rates reduce plastic leakage into the environment and decrease reliance on virgin polymer production. Increased efficiency lowers operational costs and enhances competitiveness in the market. IoT-enabled traceability certifies recycled content, boosting brand credibility and meeting sustainability demands from global brands and regulators. These outcomes demonstrate the value of integrating digital technologies into circular economy practices, supporting both business growth and environmental stewardship. Implementing IoT systems in waste management faces challenges such as high costs, legacy integration issues, and cybersecurity risks. Effective staff training on new digital tools and analytics is crucial to maximize the benefits of IoT investments. Data interoperability across supply chain partners is necessary for system-wide impact, requiring the adoption of compatible technologies and standards. Scaling these innovations also demands organizational change, ecosystem collaboration, and aligned policies among stakeholders. Addressing these considerations is essential for expanding the reach and effectiveness of digital solutions in the circular economy. Digital transformation empowers sustainable plastics management by unlocking new pathways in developing economies and challenging traditional assumptions. Industrial actors in Southeast Asia are leading innovations in circular manufacturing, integrating technology with ecological performance. IoT serves as the environmental backbone, supporting accountability, product innovation, and stakeholder trust beyond automation. Effective leadership integrates technology, operations, and sustainability to build resilient circular plastic systems. These broader implications highlight the potential for digital solutions to drive meaningful change in plastics management and support the transition to a circular economy. Digital technologies such as artificial intelligence, blockchain, and the Internet of Things enable new ways to design, monitor, and govern material flows in circular economy systems. In the European textile industry, AI and blockchain enhance product design and supply chain accountability, promoting sustainability. Blockchain fosters institutional trust and compliance in India's fragmented e-waste management sector. IoT improves operational efficiency in plastic recycling, showcasing advanced digital solutions in emerging economies. These examples illustrate how technology can empower both industry and government to address practical and systemic challenges in implementing circularity at scale. Realizing the potential of digital technologies in the circular economy requires complementary capabilities such as digital literacy, aligned institutions, regulatory innovation, and stakeholder trust. Ethical data governance is crucial, addressing issues of inclusivity and power imbalances as digital infrastructures become embedded in environmental governance. By fostering these capabilities and addressing ethical considerations, organizations can ensure the responsible and effective integration of technology into sustainability practices. Adopting a systems perspective is essential for future leaders in the circular economy. This approach encourages moving beyond tool-centric views to see technology as part of broader institutional strategies. Continuous adaptation and cross-sector collaboration are required to support regenerative economies. Leaders must be technologically fluent, ecologically conscious, and socially responsive, integrating these qualities into their decision-making and organizational practices. By embracing a systems perspective, future leaders can drive meaningful change and support the development of resilient and sustainable business models. Thank you for your attention throughout this chapter. We have explored how emerging technologies are transforming the circular economy, with a focus on artificial intelligence, blockchain, and the Internet of Things. Through detailed case studies in textiles, e-waste management, and plastics recycling, we have seen how these innovations address real-world challenges and create opportunities for sustainable practices. We look forward to welcoming you to the next chapter.